This is the second part of the second lecture of week 11, where we'll consider some examples of differential equations involving Dirac delta function. Let's look at this given example of initial value problem. And let's look at the differential equation. So here we have on the left side some function. Y is displacement, right? So y plus y double prime must be some function. And on the right hand side there is something strange. The object which is at 0 is infinity and 0 otherwise. So in fact this is almost 0, right? So this very looks like homogeneous equation, but only at the point 0 we have infinity on the right. So now in fact this is just a symbolic problem. It doesn't have any sense. Let's make sense to this problem. And to do this, let's now comes back to the definition of Dirac delta function. As you remember, Dirac delta function was introduced as a limit, as an approach to infinity, of these functions fn of t, where the function fn is just n when t between 0 and 1 over n and is 0 otherwise. And let's now consider a different initial value problem with the function fn on the right hand side. Let's say we have the same initial values, and since each time when we solve this for different n we get different solutions, let's denote the solution by yn. Okay, so let's solve this initial value problem. Okay, what we do, we can apply the Laplace transform to the function, to the both sides of the equation. So on this side we have s square yn of s plus yn of s, and on this side we have Laplace transform of this function fn, and for any fixed n this is just the this is just n minus, so this is Laplace transform. Let's rewrite this function fn using step function, okay? N minus n u t minus 1 over n. So now when we take Laplace transform of this, sorry, it should be Laplace transform, of course, at the point s. So now as we take the Laplace transform of this, so Laplace transform of n just 1 over s, right? So n over s we get here, minus, and here we obtain the Laplace transform of u at the point t minus 1 over n, which is n, the coefficient, times e to the minus s times 1 over n over s. So this is just Laplace transform of u. So let's rewrite it as n over s 1 minus e to the minus s over n. And now we can find yn of s as, in fact it's better when it's opened, the brackets I mean, minus n e to the minus s over n s squared plus 1. So we just divide by s squared plus 1 everything. And now let's come back to so we apply inverse Laplace transform, obtain y over t. So what we have to do, we have to use partial fractions to rewrite these things. And in fact for the first one, this will be for the 1 over s squared plus 1, this will be 1 over s minus s squared plus 1. So Yes, this is correct. So now we can apply inverse Laplace transform to these things. What do we obtain? N, this is the inverse Laplace transform of 1 over s minus n times inverse Laplace transform of this thing is cosine of t. So cosine of t. And the same is here, but the difference is this factor e to the minus s of n, which gives us the step function u t minus 1 over n. And in brackets, we have the same difference here. For 1 over s, this is just n. And for the second part, this must be cosine again, but cosine at the point t minus 1 over n. So by the translation formula for the step function. So yn is now this expression. Okay, let's now try to find the limit of the solutions. Let's find the limit of the solutions yn. So first of all, let me notice that if we fix some positive t, and since limit, we'll consider the limit as n approach to infinity, so n can be considered as very large number, we can assume that 1 over n is quite small number, and so at least this is less than the value of t. And under these conditions, the value of the function t minus 1 over n is just 1, right? And so y over n, here we replace u with just 1. This is n minus n cosine t minus n plus n cosine t minus 1 over n. So this is, n here can be cancelled, n cosine t minus 1 over n minus n cosine t. So we need to find the limit of this function t minus 1 over n minus n cosine t. And let me rewrite this as follows. Limit n approach to infinity cosine t minus 1 over n minus cosine n cosine t over 1 over n. And let me now, sorry, there shouldn't be n here. And let me now make a substitution. We introduce h, which is just 1 over minus 1 over n. So in this case, as n approach to infinity, h will approach to 0. And this 1 over n will be minus h. So let's write it as minus cosine t plus h minus cosine t over h. This is minus limit h approach to 0 cosine t plus h minus cosine t over h. And this is exactly definition of derivative of cosine, right? So this is minus d dt of cosine of t. And as we know, derivative of cosine is minus sine. With this minus will give us just sine t. So let's summarize what we have. So the solution, or not solution, the limit of solutions yn of the problem with the initial values just 0. Yn of 0 is y prime n of 0 is just 0 is sine t. So this is the limit of these functions yn. So we can assume now, or we will assume that sine t is solution of the initial value problem, the same initial value problem, but with delta on the right. So in fact, we define that the solution of this initial value problem is the limit of solutions of these initial value problems. And in fact, do not do this each time. We can solve this initial value problem now, because we already defined what the solution is. Just applying Laplace transform. Let's do this. Just applying Laplace transform, we get s square ys plus ys, and the Laplace transform of delta, as you remember, this is just 1. And so ys is 1 over 1 plus s squared, and so yt is just sine t. So we got the same thing as a limit of the solutions yn as using the Laplace transform approach. So we can prove, or one can prove, that we always can use this approach to solve this initial value problem. Let's now use this approach for some different example. For example, we have let's say this one, this differential equation with the initial values 1 and let's say 0 here. So what we do, we apply Laplace transform to the both sides of the equation. So here we get s squared ys plus 9ys, and this one is the Laplace transform of delta t minus p. We can show that this is in fact, so this is at the point s, this is in fact 3e to the minus pi s. So now we can find ys, which is 3e to the minus pi s over s squared plus 9. And now we apply the inverse Laplace transform to get y of t. So this is inverse 3 inverse Laplace transform of this function. And of t. And this is in fact using the translation property. This is u t minus pi, and the inverse Laplace transform of the function 3 over s squared plus 3 squared, and at the point t minus pi. So, sorry, inverse. So u t minus pi, and this one is sine, and b is 3 here. So this is sine 3t, but with this value t minus pi. So this is in fact u t minus pi sine 3t minus 3 pi, and this is the same as minus pi, right? So this is in fact u t minus pi sine 3t, just with minus in front of the function. So we can solve the problem using the Laplace transform and inverse Laplace transform, avoiding all these limiting processes.